All right, welcome back. We're going to continue with chapter 14, Fluids and Elasticity, and we're at the section of Bernoulli's equation. We derived Bernoulli's equation, and we're going to continue now applying Bernoulli's equation for 2 or 3 more problems. And after that, we will talk about elasticity, and that should end the chapter, and then we will do some end of chapter problems, practice problems. So let's read together this kind of wordy problem, and then we will draw a picture to simplify the what's going on. So let me read it first. So small hydroelectric plants in the mountains sometimes bring water from a reservoir down to the plant through enclosed tubes. So they're enclosed. The pressure inside them is not that of atmospheric pressure. At the ends of the tube, when it's open to the atmosphere, the pressure would be atmospheric. Okay. Now, in one such plant, the 100 centimeter diameter intake tube in the base of the dam is 50 meters below the reservoir surface. The water drops 200 meters through the tube before flowing into the turbine through a 50 centimeter diameter nozzle. The questions are, what is the speed of the water into the turbine, and then by how much does the inlet pressure differ from the hydrostatic pressure at that depth? All right, let's get into it. And we're going to draw a picture first. So, let's see if I can draw something good. So here is the dam, the reservoir. It's very large, and there is an opening here. There is a pipe here that flows, and then the pipe flows, and then the water exits, and then it feeds into a turbine, but it's open here. So the water flows here, the water comes in here, and this is the surface of the dam. And if we were to draw the x and y coordinates, namely the y coordinate really, I can call this here at y3. So this is y3 equals to, let's call this the 0, and v3, we're trying to find it. This point here is 200 meters above it, so this is y2 equals to 200 meters. Right? The water flows, the water drops 100 meters through a tube. I thought it was 200, maybe I wrote it wrong. 100 or 200. Drops 200 meters, so that's a typo here. This should say 200. And from here to here it's 50. So this is y3, and it is 50 meters. And here v2, I don't know what it is. I'm sorry, we call that 3, this is 2, so this is 1. We call this one 1 here. Notice the dam as it drains. Yes, it drops, but it drops really, really slowly. So approximately the speed at which the dam drains, the water velocity here, the speed, is v1, and it's approximately 0. Okay? And the first question is, what is the speed of the water into the turbine? So here, when it exits the pipe and goes into the turbine to spin it and generate electricity. So the key is, this is fluid and it's moving, and our friend will be Bernoulli's equation. So we're going to, since we want the speed here, I'm going to apply Bernoulli's equation between these 2 points, here and here. And remember what it says. It says P1 plus 1/2 rho V1 squared equals to P2 plus, nope, one more term, plus rho G Y1 equals to P2 plus 1/2 rho V3. Since we're talking about point 3, we will label it 3. So here it would be P3 plus rho G by 3. Let's take a step back and look at it. That looks correct. Now, the pressure here, P1 will be 0 because it's open to the atmosphere. And here as it exits, it's open to the atmosphere. So it's P1 and P3 are both atmospheric pressures. And so let me label it. P3 is P atmosphere. And P1 is also P atmosphere. P1 is P atmosphere. In here, it's not going to be P atmosphere because it's inside the fluid. It's not open to the atmosphere. So P1 and P3 are the same, so they cancel. We said the speed here of the fluid is about 0. So this thing is about 0. And then this one will be at here, and we label that at y equal to 0. The high is 0 there. So this is 0. So what's left is simply 4 terms drop, so we just have 2 left. So this and this. And we can divide by rho on both sides for this and this. And so we get, oh, this should say squared, not cubed. So we get V3 will equal to 2G Y1 square root. So we get 2. G is 9.8. And what is the height here? If this is the 0, this is, this is 50 meters above, so I should have labeled this. So if this is 200, this one is 200 plus 50, so this should say 250. A lot of mistakes today. Okay, that's okay, we're getting them. 250. Okay. So 250 square root. Get my calculator here. So I have 2 times 9.8 times 250, and I have to take the square root of that. Oh, that's the nicest number ever. 70. I didn't expect it to be that even. So 70. 70 meters per second. So that's the speed here with which the water exits. So to answer part B, they want to know what the pressure here compared to the hydrostatic pressure. If the dam was closed, what would be the pressure here? And then since the water is flowing, what is the pressure here? And then we want to compare them. So we will compare them in a moment. So, so let's see. So we need to find the speed here first. Let's find V2. To find V2, see, the fluid enters here and then it leaves here. So if 10 gallons, if 1 gallon per second flows into it, 1 gallon per second has to flow out. So we will use the continuity equation, which says the area here times the speed here equals to the area there times the speed there. So we would have area 2 V2 will equal to area 3 V3. And area 2 will be pi times the diameter over 2 squared, right? Pi r squared. It's circular. And so, so diameter over 2 squared. And we have done this already, but let me just label it. So area 2 will be pi diameter 2 over 2 to the power 2. And then V2. And then on this side, it will be pi diameter 3 over 2 squared V3. Remember, the pi's cancel, and when you square the 2 on the bottom, it becomes a fourth, and here also a fourth, so you multiply by 4, that goes away. And so you end up with diameter 2 squared V2 will equal to diameter 1 squared V1, and therefore V2, I'm sorry, not 1, 3. And then so V2 will be diameter 3 over diameter 2 squared V3. And so what do we get? Diameter 3 is, the diameter here is 50 centimeters. Not this one. The tube here is 50 centimeters, and the tube here is 100 centimeters. So it will be 50 over 2. 50 over 100, 50 centimeters over 100 squared times 70. So this is simply what? 50 over 2 We don't need to convert them because centimeters over centimeters, they go away anyways. So that's a half, and you square it, you get a fourth. And so 70 over 4, so you get 35, so 17 and a half. 17.5 meters per second. Let me make sure I did not make a calculation mistake. Just double check with the calculator. Here. Okay, so it looks good. Yeah, looks good. 17 and a half centimeters. So now the next thing is to find the pressure here and compare it to the hydrostatic pressure. The hydrostatic pressure, remember how it varies. You take the pressure here and add rho GH. If you just had a dam that is just locked, the water doesn't flow. So the hydrostatic pressure would just be the pressure here, atmospheric, plus rho GH. Now, since the fluid is flowing, let's find what the pressure here, P2, and then find the difference between P2 and the hydrostatic pressure. So we'll apply Bernoulli's equation again. We will say, we will apply this same equation, but here, this will be 0.1, this will be 0.2. So we'll get P1 plus 1/2 rho V1 squared plus rho G Y1 will equal to P2 plus 1/2 rho V2 squared plus rho G Y2. I want P2. And again, this is basically 0. The fluid is basically not moving at all here. It drops, but very slowly. And we have this, so let's move everything to the other side. So we get P1, okay, P1, and then rho G Y1 minus rho G Y2, that's rho G Y1 minus Y2, okay, so that's that, and minus 1/2 rho V2 squared equals to pressure 2, equals to pressure 2. Now this is the hydrostatic pressure, because what is the pressure at the bottom here? If the fluid wasn't moving, it would be the pressure here, which is P1, it's the atmospheric pressure, plus rho G times the depth. And the depth is 250 minus 200, which will be 50. So Y1 minus Y2. So this is the hydrostatic pressure. So I'm going to label this as the static pressure, P static. So let me put it this way. So P2 would be the P static minus 1/2 rho V2 squared. So the static pressure would be larger, meaning like this. P static minus P2 will be 1/2 rho V2 squared. Rho V2 squared. That's the difference between them. Because they said, by how much does the inlet pressure differ from the hydrostatic pressure? Well, the inlet pressure is the P2, right? The inlet when it goes inside here. So the inlet pressure is actually less. This minus this will be a positive quantity, meaning P2 is less than the static. So by how much do they differ? They differ by 1/2 rho V squared, so we can just calculate that. 1/2 rho, since it's water, would be 1,000. And V is, we said 17.5, so 17.5, and you have to square it. And let's get a calculator to do this. So I get 17.5 to the power 2. We divide that by 2. So I get 153 times 1,000. That's 153,000. So that's 1.53 times 10 to the 5th pascals, which is approximately how many atmospheres? One atmosphere is 1.01 times 10 to the 5th. So let's divide that by 1.01, and we get 1.51 pascals. 1.52 pascals. I'm sorry, 1.52 atmospheres. That's how many atmospheres they differ by. And you probably noticed that the pressure when the fluid is moving is less than the pressure when the fluid was not moving, which makes sense. I mean, if you shut this, it means there is a force this way that's stopping the fluid from moving. And if you open it, that pressure that backward pressure wasn't enough to stop it, so it's less. So that's why it will move. So when fluids are moving, the faster, the less pressure. I just realized the board was slightly up, so I decided to put it down so you just have a nice complete picture of everything. So let's look at this application called the Venturi tube. And this is an I. There is no C. So it looks like this. So imagine you have a tube. It looks like it's open from this side. It's open from this side. The area here is A1 and the area here is A2. And what they do is they do this. And they place an oil here, or a fluid or something, some kind of an oil. So let's say the oil will have this level, right? It will have this level. When nothing is going on, everything is atmospheric pressure. It's just atmospheric pressure. Now, what happens is, let's say you're in a plane, you're going at certain speed, so the wind enters and you want to know at what speed, what is the speed here compared to there, okay? So when the wind enters here, so let's say it's air, so this is air flowing. So remember, this is air, this is a fluid, so the density here would be density of the fluid, the density here would be the density of the air. So it enters with speed 1, V1, and so the pressure inside here at this region will be pressure 1, P1, pressure 1, and the pressure here will be P2, and the speed here will be V2. And so these two pressures will not be the same, so the pressure here may be lower than here. If the pressure here is lower, the fluid will go like that. It will rise, and we'll see why. Let's see. So it will just rise. And it will rise by an amount h, and based on that h, we can determine the speed. So let's apply Bernoulli's equation here for the air, and then we'll apply it for the fluid, and then we will see what happens. So the air is moving, the fluid is not. The fluid will just go like this, and then just sit there. So the fluid is in hydrostatic equilibrium. The air is moving. So for the air, you will have pressure 1 plus 1/2 rho air. Let me put here rho air. Okay, air. V1 squared plus. They're at the same height, so I will just. This will be y and this will be y. So that rho gy. If you like, you can put y1 and we will write the same y1 on the other side. Yeah, sure. Let me write it as. I will just write it as y because they're at the same height. This is the same level. And then here would be P2 plus 1/2 rho air V2 squared plus rho gy, just rho gy. So this simply goes away, and here pressure 2, pressure 1, they are related to each other. And so I can also, since the area here is area 1, you know the area of this tube, so you can find the relationship also between the speeds. So we can also use, so this is the first equation. The second equation we will use is area 1 V1 will equal to area 2 V2. Okay? So V2 will be area 1 over V1. Okay? So area 1, V1, so V2 will equal to that. Now, let me also write, let's see, the pressure here P1, the pressure here is P1 also, I'm sorry, P2, and so let me just, let me erase this one and make it a little, I will rewrite it again in a moment. So I will have P1 minus P2. I'm going to move P2 here and then everything else to the other side. Will equal to what? 1/2 rho air V2 squared minus V1 squared. V2 squared minus V1 squared. Okay? So I have this equation here. And I also have, so maybe I should put the star here. So this is the equation I have. Now the continuity equation will tell me V2 will be this, A1 V1 equal to A2 V2. Okay, and so if so I can have this V2 will be A1 over A2 times V1 times V1, and I can plug it over there. So let's see what happens when we plug it. When we plug that here, so we get P1 minus P2, P1 minus P2 equal to 1/2 rho air. You see what? I don't know the speed here. I don't know the speed here, but this is measurable. Imagine you're flying or something, and you have the speed here. I'm sorry. You can measure h because you can view it. You have a ruler, or maybe it's labeled. You know the density of the oil here, or the liquid that you have. You have, so this is the liquid. You have the density of air, it's 1.29, and you know the areas. So we want everything in terms of areas and h and the densities, okay? So we will write here 1/2 rho air, and then V2 squared. Well, V2 squared would be A1 over A2 squared, and then V1 squared minus V1 squared. So it would be this. A1 over A2 squared, V1 squared minus V1 squared, like so. And let's factor the V1 squared, so we get P1 minus P2 will equal to 1/2 rho air times this, area 1 over area 2, the whole thing squared minus 1, because I factored the V1 squared, and I'll put it here, V1 squared, like so. All right, so let's put a box around this. So now the only thing undesirable here is I have the V1. These are measurable, but these two, I don't know what they are. But let's go to the fluid now, right? The fluid. So the fluid is in hydrostatic equilibrium. It's in equilibrium, it's not moving. So we know that the pressure differ by depth. The pressure here, so P2, you see the bottom here, it has to have the same pressure, otherwise the fluid will move. It has moved and it's in static equilibrium, so it's there. So the pressure here has to equal to the pressure here. As we go higher, let's say we start here and here, that's the same pressure. As we go higher, it would be the same pressure up to this point. So this is P1 here. As you go higher, it gets lower and it gets P2. So the pressure here, the pressure at this level, which is P1, it's equal to P2 plus rho liquid. I'll put here fluid, rho fluid times gravity times the depth, this h, which we can see. So from this equation here, we also have, so for the liquid, for the fluid, you have P1 minus P2 will be rho fluid GH. Rho fluid GH. And you can see P1 minus P2 now over here can be eliminated by this. So we get, so set them equal. So instead of P1 minus P2, I would replace it by rho GH over there. So I get rho fluid, remember, it's fluid, G times the height will equal to 1/2 rho air, and then what? Area 1 squared over area 2, or area 1 over area 2 squared minus 1, and then V1 squared, and we can solve for V1 now. So multiply by 2, divide by the density of air and this stuff, and take the square root. So V1 will equal to 2 rho fluid GH divided by the density of this air, and then here I have the area 1 over area 2 squared minus 1, and you take the square root. All right. So that's V1. Let me make sure I have it. Correct. It looks correct, except they just have it in a different. They have it in a different format. So yeah, let me just write it in the format they have. They just split this. They put it A1 squared and then A2 squared. Found the common denominator, so you multiply this by A2. And the A2 goes upstairs and you take the square root, so the A2 comes out. So you get this. So it reduces to this. V1 will be, so the A2 comes out, times the square root of 2 rho fluid G times H divided by rho of the air, and then times A1 squared minus A2. A2 squared, like so. Okay. Hopefully now it looks correct. So that looks good. And then V2 is what? It's A1 V1 over A2. So when you multiply by A1 and divide by A2, the A2 goes away and just the A1 comes out. So just you have the A1 times this stuff. 2 rho fluid GH divided by rho air, A1 squared minus A2 squared. So this is just an apparatus that you can use it to measure the speed of air. So let's say you have this Venturi tube and it's windy, and you want to know the speed of as the wind enters your this whatever pipe that you have. You want the speed of the wind. Or somebody blows into it, and so what you see is the fluid rises. And you see again, the region where the speed is lower, you see this is bigger area, so the speed here is lower than here, where the speed is higher, the pressure is lower, and where the speed is lower, the pressure is higher. Okay, I will pause this one, and we will start again in the next video. So we're going to discuss next elasticity and Young's modulus. It's going to be it's a quick topic. It's not that long.